Hello and welcome to another WJEC A level physics question. This was question 7 from January 2012's Unit 4, and it's a question about star systems basically. This is nowadays still found in Unit 4. So what we've got is light from a distant star arrives at the Earth, and the star and planet are revolving around the centre of mass of the star-planet system as shown on the diagram. And the scientist analyses the light and draws the following graph of results. What we've got here is a wavelength shift graph showing the Doppler shift of the wavelength of the light from the star as received at different times during its orbit. Now we're going to use an appropriate value from the graph to show that the orbital speed of the star about the centre of mass is approximately 12 meters per second. So what we're going to use here is the Doppler shift formula. Delta lambda over lambda is V over C. So V is delta lambda over lambda times C. So let's put in values. Now delta lambda, if we read off the graph up here, is 2.5 times 10 to the minus 14. And the original wavelength was 650 nanometers, so we mustn't forget the 10 to the minus 9. Times 3 times 10 to the 8. We put those numbers into the calculator, we end up with 11.5, so near enough to 12 meters per second that we're asked for. For the second part of the question, we're going to use the period of orbit of the star to calculate the radius of the star's orbit. Well, here we can use the idea that simply speed is distance over time, where the distance is the circumference of the orbit, 2 pi r, and the time is the period of the orbit, capital T. So if we rearrange that equation, we get that r is equal to vt over 2 pi. So we've got 11.5 times the period. Now if we read the period off the graph, going from 0 to here, we've got ourselves near enough 9.8 years. And that's important that we remember that this time has to be in seconds. So 9 times 365 and a quarter, you can just call it 365, it's not going to make too much difference, times 60 times 60, so turning the years into days. Oh, and sorry, there's a times 24 in there as well. Years into days, days into hours, hours into minutes, and minutes into seconds. So put all those figures into the calculator, and we end up with 5.68 times 10 to the 8 meters. The next part of the question tells us that the mass of the star is 2 times 10 to the 31 kilograms. We've got to show that the distance between the star and the planet is approximately 1.5 times 10 to the 12 meters. So show your workings clearly and state any approximation that you make. So the approximation that we're going to make is that the mass of the planet is much less than the mass of the star. And then we're going to use the t equals 2 pi root d cubed over g m1 plus m2 formula. But here, because the mass of the planet is very much smaller than the mass of the star, this will simplify to t equals 2 pi root d cubed over g, just ms, if you like, mass of the star there. Square both sides. I'll do lots of algebra here to show you the steps. We get t squared is 4 pi squared d cubed over g, mass of the star. And we're trying to find here d. So d is going to be t squared times g times the mass of the sun, all over 4 pi squared and square rooted. So if we put in our figures, we've got the 9.8, let's put that square root symbol, sorry, cube rooted. Let's put the period back in as 9.8 years. For that squared, times 6.67 times 10 to the minus 11 for g, times 2 times 10 to the 31 for the mass of the star over 4 pi squared. Now it tells us that the answer should be about 1.5 times 10 to the 12, and if we do put those numbers into the calculator, we get 1.48 times 10 to the 12. I'll squeeze the answer in here. Next, we're going to calculate the mass of the planet. So here we can use the centre of mass formulae, where we have things like R1 is M2 over M1 plus M2 times D. But we're allowed to carry on with that same approximation, that the mass of the star is very much greater than the mass of the planet. So the mass of the planet here will be M2. The bottom of this equation will simplify just down to M1. So a quick bit of rearrangement. M2 is R1 times M1 over D. And if we put those figures into the calculator, let's put them into the equation first of all. R1, what we worked out in an earlier part of the question on part B, was 5.68 times 10 to the 8. M1 is the mass of the star, and D is our 1.48 times 10 to the 12. So let's put those into the calculator. And we end up with 7.7 times 10 to the 27 kilograms. Which is thousands of times smaller than the mass of the star, so the approximation was a good one. The last part of the question goes back to AS physics with the radiation from stars work. It tells us the luminosity, or the radiation power output of this star, is 3,000 times greater than our Sun. However, the planet is 10 times further away from the star than the Earth is from our Sun. We've got to explain briefly whether or not the temperature of this planet is similar to the Earth. So the intensity formula from AS was one that you had to learn, I equals P over 4 pi r squared. If we look at the two factors here, what we've done is we've multiplied the power by 3,000 and we've multiplied the radius by 10, so we've got a 10 squared factor here. So if we factor in both factors, we've got that the intensity at this new planet, let's call it EIP if you like, is going to be 30. 3,000 divided by 100 is 30 times the intensity at the surface of the Earth. So therefore this planet is hotter than the Earth. Thank you very much for listening. Please remember to like and subscribe, and feel free to ask any questions. Goodbye now.